Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're very happy to have Charles Smart from NYU, soon moving to MIT, who will tell us about scaling limits of the Abelian sandpile.
Great. Well, thanks for the invitation. All right, so I want to talk about scaling limits of the Abelian sandpile. So before I actually started on the math, I should mention that most of what I'm going to be talking about is joint work with Wesley Pegden, who's at NYU. And a little later, if I actually get to it, it's also joint work with Lionel Levine, who's here in the audience, and you're at MIT now and moving to Cornell, right? Yeah. Okay. So, all right. So to start, I want to give a little bit of an introduction. I know that probably most of you are already familiar with the sandpile, but I guess for our viewers at home, I'm going to try to start from a little more basic point. Okay, so I want to start just by talking very briefly about internal DLA, which I think is sort of the natural precursor to the sandpile. So you guys may disagree about this, but somehow this is how I ended up thinking about it. Okay, so what is internal DLA? So internal DLA, or internal diffusion limited aggregation, is sort of a growth process for subsets of the integer lattice. Okay, so this is a diffusion driven growth process. For subsets. So can you guys all see this? Yeah. Okay. For subsets of the integer lattice z to the d. So the d-dimensional integer lattice. So what's the idea? Well, you have some subset, and maybe this thing is going to be in the way now. Can you actually see if I write down here? Probably not. Okay. Well.
Two more lines we can see.
Two more lines. Okay, well, I'll try to stick to this little area. I guess I should try to very quickly get to the part where I want to actually show the important picture, and then we can get rid of the screen. Okay, so what's the idea? Well, you take some subset of the lattice, so I can only draw two-dimensional pictures, but the idea is you have some subset of the lattice, some subset A of z to the d. Okay, and you grow this set by sort of dropping a token somewhere on one of the vertices inside, and then you run a random walk. So you let that token walk randomly on the lattice until it exits the set. Okay, and then you add that exit vertex to A. Okay, so the idea is, let's say we start with A0 just being the set that contains the origin, and then we let the next set be, well, the first set union the exit vertex of a random walk from the origin. Okay, so you just iterate this process. Okay, well, because a random walk in the integer lattice sort of looks like Brownian motion if you zoom out, right, we'd expect that this thing is going to be spherical looking. Right? The set will be spherical looking. And in fact, that's exactly what happens. And, well, if you rescale it properly, it really does converge to a sphere. So what is the proper rescaling? Okay, so if we define this sort of a rescaled set A to be, well, the set of points in R to the D, so that, well, n to the 1 over d power times x is in an. Okay, well then for a certain notion of convergence of sets, what we get is that these rescaled guys converge to, well, the ball of radius, I think this is to the ball of radius, the volume of the ball to the minus 1 over d power. I think this is right. Okay, almost surely. Okay, for some appropriate notion of convergence here. Okay, so I want to think of the sandpile as just a deterministic version of this. Okay, so the idea is that, well, instead of actually having a random walk, okay, what we're going to do is we're going to, okay, so I can imagine this has a sort of a token arrives at a point and then it just jumps to a random neighbor, right? And that keeps happening until that token gets outside the set. Okay, instead what I'm going to do is I'm going to have it be the case that a vertex sort of just stores tokens, okay, until it has at least as many tokens as there are neighbors in the lattice. Okay, and then when it has at least that many tokens, it just distributes them all at once to all of its neighbors. Okay, so the process is, so the way you build the sandpile, okay, is you start with sort of n tokens or chips at the origin, okay, and then you iterate this process where if some vertex x in z to the d has at least 2d tokens, then we topple x, okay, by removing 2d tokens from x, okay, and adding one to each of its neighbors. Okay, and there are 2d neighbors, right, on the d-dimensional lattice. Okay, so what happens? We keep doing this until it stops. All right, and we get some final configuration, Sn, mapping z to the d into, well, the possible numbers of tokens for a stable configuration. So every vertex has to have between 0 and 2d minus 1 tokens left over. Okay, so if we did a good job of actually making internal DLA deterministic, then we'd expect that the result would be a circle. Right? You expect the result would be a circle, and that maybe which value you take when you're inside of the circle would be kind of randomly distributed, right? And of course, this fails spectacularly. So we have this picture of what the final sandpile looks like. So maybe I'll look at a low-res one first, which my laptop doesn't want to display. Okay. Okay, so this is just one with 1,000 chips. So if you start with 1,000 tokens at the origin and you run the process, you get something like this. Okay, but as you add more, it gets a little more refined. So you get sort of a kind of stranger and stranger looking picture.
Shade of gray is density.
That's right, yeah. So here the shade of gray is just the density. So black is, in this case, 3 chips, and the dark gray is 2, and the light gray is 1, and white is 0. And then I guess maybe it's a little difficult to tell, but all of the sort of light-colored specks in here are actually light gray. The only zeros are outside. Oh, no, wait a minute. No, there are zeros in there. Okay, so then finally, if I just load a really high-res one, we get a picture like this. Okay, so this is 16 million starting nodes. We get this picture, which, okay, so I want to point out a couple things. So first of all, it is definitely not a circle, right? You can see that there are sides, right? So it's flat on the bottom. I guess maybe full screen mode is not so great. Okay, so it's actually flat on the side on these sides here, right? So you get this what looks to be like a 12-sided figure, right? Except that these things maybe are slightly curved. Okay, and then of course on the inside, it doesn't look at all randomly distributed, right? There are these regions where you just get solid 3s, and then if you zoom in, okay, to some region where there aren't solid 3s, what you see is that rather than having sort of solid 3s, what you have is some sort of solid periodic pattern, okay, in these other regions. Okay, so this is not at all what you would like to get if you were actually just trying to make a deterministic version of internal DLA. Okay, so what the heck did Wes and I prove? Well, oh man, this is just not working at all. I apologize. Well, the pictures will soon go away, and what?
16 million is too much.
Oh, this was 32 million. Oh, okay. Maybe that's the problem.
It's a Mac.
Yeah, exactly. I think actually the hard drive is failing on this thing, so that's probably what's going on. Okay, well, so I guess I'm done with the screen, so I don't know how. Great.
So we get one request. You could have said I want $1 million.
Okay. Yeah, I said the wrong thing. Okay, so what the heck did Wes and I prove? So I guess actually one thing that I didn't point out when they had those pictures up there is that as you add more chips, sort of the picture gets more and more refined. Right? It doesn't change that dramatically as you add more chips. In fact, it seems like the image is actually converging to something. Okay, and this is what Wes and I did. So we figured out that in fact there really is a limiting image. Okay, so I want to explain how we did that. Okay, so let me talk about that. Okay, so in order to explain the proof, I need to give a little bit more background about the sandpile. See another?
Before you give the proof, maybe could you clarify the statement of what kind of convergence you mean?
Yeah, exactly. So that's part of what I need to talk about. Yeah. So let me first give a little bit more background. Well, okay, I guess you know what? I can tell you the notion of convergence now, if you want. Okay, so if you remember, for internal DLA, well, in order to get the set to converge to a ball, we had to rescale, right? So you need to do the same kind of rescaling here. Okay, so there's this final configuration. Okay, after you run the dynamics. Okay, when you add n chips, you get some map from z to the d into 0 through 2d minus 1. Okay, but this map, sort of the support of this map is expanding, right? It's blowing up as n goes to infinity. Okay, so we need, in order to keep it bounded, okay, we have to rescale it. So the idea is, okay, well, we're going to rescale like this. So we're going to set S bar sub n of x to be Sn of, well, h inverse x, okay, where h is n to the minus 1 over d. Okay, so now this guy, this Sn bar, well, this is a function from h z to the d into 0 through 2d minus 1. Okay, so they're defined on sort of ever finer lattices.
So there's some rounding in the, right?
Some rounding.
X need not be in the lattice.
But now it is, because x is in this h.
Right, so like this argument is supposed to be in this set.
Oh, I'm sorry.
Right, so then you hit it with h inverse and it goes into here. Yeah. Okay, so if we do this, actually, well, Sn is going to stay bounded. So the support of this guy is compact, okay, or sort of independently of n. Okay, and even better, you can check that the mass is constant. Right? Okay, so the idea is and here I'm integrating over r to the d. I'm sort of abusing notation a little bit, but the idea is, okay, if I have some function on the lattice, I'm just going to make it piecewise constant in a little square around each lattice point. Okay, so if I rescale like this, the mass stays constant, okay, and the support stays bounded. Okay, so what Wes and I can prove is this. So theorem, this is Pegden and myself. Okay, is that, well, there exists, so there's a function s, which is in, L infinity on r to the d, okay, and it's bounded, so it's a measurable function. It's between, its value stays between 0 and 2d minus 1. Okay, and these guys converge weakly, star, in L infinity to s as n goes to infinity. Okay, so what the heck does this mean? Okay, what this means is, so that is, okay, if I integrate against a test function, I get convergence. So the integral of Sn bar times some test function phi converges to the integral of s against that test function as n goes to infinity. Okay, for all test functions, so all continuous functions, or you could even just take smooth functions, okay, on r to the d that have compact support. Okay. Okay, so this is a weak notion of convergence. Okay, it says nothing about what's actually happening to the values. Okay, but it really is the correct notion of convergence for this problem. Okay, and the reason is that, well, the values of these Sn bars really don't converge to anything. And the reason is that, well, if you look in the sandpile, okay, if you actually look at those images, well, okay, there are regions where Sn bar is piecewise constant, right? It's like there are these regions where it's solid black, where it's all threes. Okay, and in those regions, it does converge pointwise. Okay, but in other regions, you have these rapidly oscillating periodic patterns. Okay, and in those regions, well, as you rescale, so as Sn gets bigger and as n gets bigger and bigger, okay, well, those patterns stay the same, but you're sort of zooming out on the pattern, right? And what happens is, in the limit, these patterns are replaced by their average value, rather than any of the individual values. Okay, and that's exactly what this notion of weak star convergence captures. Yeah?
So here's a question. So here's a stronger type of convergence, which it seems ought to be also true, whether you know this or not, that the proportion of zeros and ones and so on converges.
Okay, so yes, that's true, but I have no idea how to prove it. Yeah. But that's definitely true, sort of, at least on a open set of full measure. That's true, but I don't know why. I don't know how.
Empirically, from looking at the pictures, or you have some reason as well?
Yeah, we had, There's a little bit of additional secret evidence that we have that hopefully I'll get to later. Yeah.
So this is just the average height.
That's right. Yeah, so you just get the average height. Okay, so I want to try to explain how you prove this. Okay, so I guess I didn't actually mention this before because I got distracted talking about the statement of the theorem. Okay, but so the dynamics. So the reason this thing is called the Abelian sandpile, all right, is because the dynamics are Abelian. So if you remember when I wrote down the definition, I said, okay, well, you iterate this process where if some vertex has at least 2D chips, you topple it, right? But that doesn't specify the order in which you're supposed to topple the vertices. Okay, but it turns out the order doesn't matter at all. And so this is what is meant by saying the process is Abelian. Because all that actually matters in determining the final configuration is just the number of topplings that occur at each vertex. Okay, so I want to just mention some more background before giving the proof. Okay, so the final configuration, okay, Sn from ZD into Z. Okay, well, not into Z, but into the interval. Okay, this guy is determined, okay, by the odometer function. Okay, Vn. So this guy is a map from ZD into, well, the non-negative integers. Okay, so what does this guy count? Well, this just counts the number of tuples. So the number of tuples at each vertex. Okay, and well, so from this odometer function, so from this function which counts the number of tuples, well, you can compute very easily the final configuration. So the final configuration is, well, it's just the initial configuration. So n chips at the origin. So I'm using this for the indicator function of the origin. Okay, plus the redistribution caused by the odometer function. So this is the discrete Laplacian of the odometer function. Okay, so what's this guy? So the discrete Laplacian is just the sum over all of the neighbors in the grid, okay, of the difference between that neighbor and the center. Okay, like this. Can you guys actually see this past the podium? Okay. Okay, great. So because the process is abelian, all we actually care about is the odometer function. Okay, and you can find the odometer function essentially by just, well, I mean, you can run the dynamics, and what is that doing? Well, so the idea is you're just taking the maximum of all of the legal odometer functions. Okay, so if you have some legal odometer function, so some number of tuples that you've achieved so far legally according to the dynamics. Okay, well, either the configuration is stable, or you can increase the odometer function somewhere, right? You can topple again, right? And so you just kind of build up the odometer function until you can't make it any larger, okay? And that gives you the final odometer function. Okay, so Lionel and Yuval in a paper together, actually, or was this one was also with Anne Fay, right? What they did is they figured out basically what the dual of that sort of construction is. So rather than trying to take the maximum of all of the legal odometer functions, okay, what you do instead is you take the minimum of all of the stabilizing odometer functions. Okay, so what they figured out is that this final odometer function, so this is Fay-Levine-Perez. Okay, what they figured out was that you can write the odometer function as the minimum, okay, so rather than maximum, okay, over all functions, integer valued functions on the lattice, okay, such that two things are true. Well, it has to be non-negative, okay, and it has to be stabilizing. So what does that mean? Well, that means that if you take the starting configuration and you redistribute it according to W, that this better be less than or equal to 2D minus 1 everywhere. Okay. Okay, so they figured this out, and this is basically the starting point for our proof of convergence. Okay, so what's the idea? Well, okay, so in some sense this is like the dual of the dynamics. It's some sort of like linear programming dual of the dynamics. Okay, but you can also think of it as sort of a discrete elliptic obstacle problem. Okay, so the idea here is, well, we want we want W to be, we're looking at the minimum of all W, okay, which are sort of discrete superharmonic with a certain right-hand side, okay, which are also greater than or equal to some obstacle, right? So this is a discrete elliptic obstacle problem. Okay, because we have an obstacle here, Okay, and here we have sort of an elliptic differential inequality. Okay, albeit a discrete one. Okay.
You're planning to say the word least action principle?
Oh yeah, that's right. This is called the least action principle. Yes. Yeah. The idea being that W is sort of, measuring the total action, right? So the number of toples is in some sense a measure of action or activity, and then you're trying to do the least amount possible.
Since this is
Yes.
going to be on the web, do you also want to mention DAR? Is it related? Isn't this DARs?
I know that it would.
I don't know.
So, is it different from DAR's least action principle?
What?
Yeah. Whoop. Yeah. Okay. So we have this least action principle. Okay, so the idea is, well, if I were just to sort of draw a picture, what do these things actually look like? Well, so I have 0, and the function sort of comes in and it lifts off 0, and it has this cusp up here. So this is sort of what a typical Vn looks like. Right, so the idea is, well, it's going to be, it's actually going to be equal to 0 outside of some radius. Okay, and then at the origin, it's going to have this cusp, okay, because of this n delta naught sitting here. And everywhere else, it's going to be kind of curving up as much as it possibly can. Okay, so how much it's allowed to curve up is determined by this 2d minus 1 here. Okay, and so it's trying to curve up as much as possible, because if you can curve up more, you can get lower, right? So if I were to increase the curvature, the allowed curvature, I could get a function which stayed in here, right, and just was much more curved and still had sort of the same angle in the cusp. Right? Okay, so it's sort of trying to bend up as much as possible here so that it can get as low as possible. Okay, but it's pushing up against this obstacle, the 0 obstacle here, right, and that's sort of what actually keeps it up. Okay, great. So now I already talked about the rescaling for the sandpile. So there's this way that you need to actually rescale the final configurations in order to get convergence. And along with that rescaling, there's a natural way to rescale the VNs. Okay, so if you remember, we had H being n to the minus 1 over d. Okay, Sn bar is Sn H inverse x. Okay, and then the natural rescaling that you get for V, okay, for the odometer function looks like this. So we do H squared Vn H inverse x. Okay, so why is this the natural rescaling? Well, it's the natural rescaling because it preserves this calculation here, right? So what it does is it lets us write Sn as, well, n times a Dirac at the origin plus the H discrete Laplacian of Vn. Okay, where this guy, this is exactly what you would expect. Okay, so this guy is just defined to be, well, 1 over h squared times the sum over all the neighbors of x of the difference between you and your neighbor, like that. Okay. Okay, great. So there's this natural rescaling to pick for V that preserves this. And then we still get a least action principle for this guy. Okay, so this guy is still the minimum over a certain set of functions, but now we have to change which lattice we're working on. So now W goes from hz to the d to h squared z. Okay, and we have the same sort of constraints. So something like that. So we have a rescaled least action principle that goes along with it. Okay, great. So I guess I need to hurry up a little bit. Okay, so how do we get convergence? So the idea is, well, what we're going to show is that there's a unique limit for these rescaled odometer functions. Okay, and from that, using this calculation here, okay, we'll get that there's actually a unique limiting sandpile. Okay, and the idea is, well, just to import techniques from PDE, from the theory of elliptic obstacle problems. Okay, so there's sort of two steps to this process. So the first thing that I need to do is I need to, actually check that, there is a sort of a limit at all for these guys. Okay, so how does that work? So I first want to talk about convergence along subsequences. All right, so this has sort of two ingredients. So the first ingredient is, so Lionel and Yuval already did a lot of the work for us, in that they showed that these guys, these functions, are sort of equibounded away from the origin. Okay, so what they showed is that, so Vn is bounded independently of n, okay, in any compact set K, okay, that doesn't contain the origin. So any subset of r to the d minus the origin. Okay. Okay, so they showed this in their paper on the strong spherical asymptotics. Okay, I guess you guys didn't quite state it like this, but what you have there implies this very easily. Okay, so we have this, and from the least action principle here, we know that, well, the discrete Laplacian, the H discrete Laplacian of Vn is between 0 and 2d minus 1. Okay, so what does this tell us? Well, it tells us that, okay, the value is bounded, okay, and the discrete Laplacian is bounded, okay, in any compact set away from the origin. Okay, and so from that, what we get, so from that we get basically for free from sort of standard theory of finite difference schemes, we get regularity estimates for Vn. So from this, plus some standard theory of finite difference schemes, okay, we get something like, so one thing you can prove, for example, is that, if you pick this compact set K, okay, then you have something like this. You get some kind of Holder continuity. So, for example, it's easy to prove this with 1/3 for the Laplacian. This is for all x, y, and k. Well, okay, I mean, it's like there are a bunch of textbooks that you can dig this out of. For example, papers by Trudinger and Kuo, I think. They have these, they have some nice papers for actually much more general finite difference equations than this that give you things like this. Or if you want, I mean, this is actually just kind of a fun exercise. You can do it in a few hours. It's not that bad. Okay, but so you get this, and this is enough to apply the Arzela-Ascoli theorem. Okay, so this is enough to run Arzela-Ascoli. Okay, so what you get is that, well, for every sequence, let's say nj going to infinity, okay, there is a subsequence, so njk going to infinity, and a function v, which is continuous on r to the d, take away the origin. Okay, remember, all of this was away from the origin, such that the rescaled guys, v, n, jk, converge locally uniformly to v. As j goes to infinity, or sorry, as k goes to infinity. Okay. Okay, so from these sort of standard find difference techniques, we get at least convergence along subsequences. All right, so then the question is, well, is this continuum limit unique? Okay. So how do we do that? Well, sort of as a first attempt at trying to get uniqueness, so I feel like sort of the natural thing to do is to, well, look at this least action principle. Okay, so we know that the Vn satisfy this. Okay, so some sort of continuum version of this is going to be inherited by this limit. Okay, and hopefully we can find a continuum version that's inherited, which gives uniqueness. Okay, so sort of a first attempt, okay, would be to just set h to 0 in here. Right, so we just send h to 0. So we could try to show this. So we could try to show that v is equal to, to v star, which is the inf over all w. So this is going to be continuous in r to the d, take away the origin. Okay, such that w is greater than or equal to 0, and delta naught plus Dirac w is less than or equal to 2d minus 1. Okay, where this time I mean an actual Dirac delta, so maybe I'll put a little hat over it. So this is a Dirac mass, not just the indicator function of the origin. Okay, so it's the limit of this guy, right? Okay, so we get basically for free that the limiting v satisfies these constraints. Okay, and because v star is computed by infing over all those things, we get immediately that v star is less than or equal to v. Okay, so we get this for free. And now we ask, okay, is v star greater than or equal to v? Right? And the answer is sort of immediately no, or at least it better not be, okay, if the pictures are correct. And the reason is very obvious. The reason is just that, well, this equation here, this constraint, is radially symmetric. Right, so if you take any function w satisfying these two constraints, well, you can rotate it any amount you want around the origin, and it's still going to be in this class. Right, so this infimum is going to be radially symmetric, right? Okay, but we know that the limiting image isn't, right? So this can't be right. Right, we know from the pictures that
We don't actually know rigorously.
right, we don't actually know rigorously. Right, so we don't know rigorously, and right, so I don't know how to prove this. Actually, well, okay, I might know how to prove this is not true. I'm not totally sure. Okay, so in any case, this is a bad first attempt. Okay, so how do we make it better? Okay, so what we're going to do is just use a simple idea from viscosity solution theory. Okay, so I think I told this story before at MIT, but for me this is kind of a natural thing to do because I learned about this whole problem from Lionel and Yuval, who gave talks at a conference about obstacle problems in viscosity solution theory. So after I saw this, it was quite natural to sort of go back to NYU and talk to Wes and try to make this work. It's like how if you're taking an algebra class and you just learned about CELO subgroups this week, then probably the homework exercises require that you use the CELO theorems. So So I was like, okay, well, you know, I have to use viscosity solutions somewhere. All right, so how do I use them? Okay, so what do we do? Okay, I mean, it's a pretty naive thing to do. So the idea is, well, let's suppose I take a smooth test function. Okay, so suppose I have some smooth function on r to the d. Okay, and suppose this smooth function touches the limiting v at some point x that's not the origin. So the picture is, you know, I have this this v sitting here, okay, you know, going up to infinity, and I touch it from below at some point x, which is not the origin, where the vertical asymptote is, with v. Okay. Okay. So what I want to ask is, well, sort of, what does this tell me about the Hessian of phi at x? Okay, so this is what I want to know. All right. Well, okay, I don't really know very much about v. Okay, but I do know. Well, I know one thing, right? I know that sort of in a little neighborhood of x. Okay. Well, I know that these approximations, okay, are converging uniformly, right? So I can pick a little finite approximation here. Okay, some v bar and j, k, for some big k, that's sort of sitting close by, and by maybe adjusting phi a little bit, I can get it to touch the finite approximation if I want. Okay, and so I want to try to use this to sort of read off information about the Hessian. Okay, and if you're sort of careful about how you sort of zoom in, so you blow up at this point, and you're careful about how you choose these representatives, what you can prove is the following. Okay, so what we can prove is that, right, so here's what we can show. We can show that, so for every epsilon greater than or equal to 0, okay, there is a function, a global function, from zd to z, so a global integer valued function such that two things are true. So the discrete Laplacian of u is less than or equal to 2d minus 1 everywhere, okay? So for all y, and this function majorizes the quadratic form you get from this second derivative, from the Hessian. Oop. Okay, so we get something like this. Oh, yes, minus. So I have to subtract off. I have to lose a little something. I think actually we don't need this. We think we can do this with a linear factor, but I know this is true, at least. So if you subtract off a little bit, right? So if you make phi a little bit steeper here, okay, then you can zoom in and rescale properly and get sort of a global integer function which beats it everywhere, whose curvature is not too big, right? Whose discrete curvature is not too big. So this is for all y and z to the d. Okay, so now I want to turn this into a definition. Okay, so I want to actually write this as a set. So I want to think of this. I'm going to define gamma to be the set of symmetric d by d matrices, okay, such that this is true, where I put this matrix here. Okay, and what I get from this calculation is that the Hessian is in this set gamma. Okay. Okay, so this gives me a new candidate for the obstacle problem. Okay, so is everyone happy with this definition? There are two quantifiers, right? So it takes a little while to read. But so the idea is just, if you bend the quadratic form down a little bit, then you can find this global integer valued function that beats it. Okay, sort of like a global odometer function that beats it. Okay, so now what's the new candidate? So this is the second attempt. Okay, so this new candidate is we're going to inf all of the w that are continuous on r to the d, take away the origin. Okay, such that, well, w is non-negative, and we're going to keep this constraint with the Dirac, so we also know this. Okay, and then we're also going to include this thing. So I'm going to use kind of funny notation. I'm going to write d2 minus w is contained in gamma. Okay, and what this minus is supposed to mean is that, well, you're only supposed to interpret this in the sub-solution sense. So let me just explain what this notation means. This means that if phi is smooth and touches w from below at some point x, then the Hessian of phi at x is in gamma. Okay, so that's what this funny notation means. Oh, really? Okay, well. Okay. Well, in the interest of time, they have to ask me afterwards. That's okay. Unless you really, anyone really want me to rewrite it? Can I just move this?
No.
Even if I just hit it really hard?
No, don't.
Don't do that. No, okay. Okay, but you can at least see this this notation, right? So this just means anytime you can touch w with the smooth function from below, the Hessian of that smooth function at the contact point has to be in gamma. Okay? Okay, so in the last, I guess, am I allowed to go through 5 minutes over since I started 5 minutes late? Yeah, okay. I don't want to, no one likes talks more than 50 minutes. Okay, so I claim actually now we get uniqueness. Okay, so from the calculation that I just talked about, well, we know again that v star has to be less than v. Okay, so now the question is just what about the other direction? Okay, so what we're worried about is that somehow this fails, right? So let's suppose for contradiction, okay, that we have some point y where this guy is strictly smaller. Okay? Well, okay, so now at this point I need to, sort of brush under the rug even more details, but sort of a standard sort of regularity theory for the Laplacian lets us do the following. So if this happens, okay, then sort of by a theory for the Laplacian, which I don't want to talk about. Okay, what we get is that we may select a point z, which is not the origin. Okay, such that what happens? Well, the second derivatives of v and v star exist. Okay, and even better, what I know is that the second derivative at v star is strictly less than the second derivative of v at z in the matrix order. Okay, so meaning that this minus this is positive definite. Okay, so the picture is something like this. Well, so maybe I should mention, so this is non-trivial, so why am I saying, these things exist? And the reason is, well, okay, we're just infing over continuous functions that satisfy some differential constraint. And sort of a priori, we have no idea if this thing is even differentiable. Right? And here I am asserting there are points where there are second derivatives. Okay, so it takes a fair amount of machinery to make that work, but it's something you can just read out of a textbook. Well, not a very nice textbook, but still a textbook. Okay. So, what? So I think actually the only place I know, so you can get this out of Hormander, or you can read textbooks on like operator, on singular operators, and and sort of get it from there. Or at least those are the only two places that I know of to find it. Okay, so what's the picture? So the idea is, okay, we have our V sitting here, and somehow V star has managed to get below it, right? So V star is coming in here like this, right? Okay, but in order for this to happen, so there has to be some point, let's say right here, where V star is curving up more than V above it, right? Because if it weren't, the inequalities would have to go the other way. Okay, so there has to be this point where this thing is steeper, is curving up more. Okay, so the idea now is, well, if I took sort of a piece of this guy around here, some piece where it really looks like its second derivative, and I translated it up here, it would sort of cut in like this.
You said, suppose
V star is strictly less than V.
Right, but then in your picture you got the second derivative to be, for V star to be bigger than for V, but...
That's right, that's what's supposed to happen. Oh, did I?
You wrote.
Yes.
Okay, good.
My apologies. Yes. Okay, so it's supposed to be like this.
Much better.
Okay, so if I took a piece of this guy and moved it up, it would sort of cut through like that. Okay. So now if these guys were both somehow, if these were the finite difference approximations, these were actually the V bar sub n's for some big n, then this would be a contradiction, because what I'd be able to do is sort of inf V with this piece of V star, okay, and that would allow me to make V lower, right, and still be in the same class, meaning that I've contradicted the least action principle. Okay, but we can actually make that happen. So what do? Well, we pick some very close finite difference finite approximation of V. Okay, so you pick some approximation of V that's very close here. Okay, so V, this is V bar sub n kj for large j. Okay, and then what I do is I take the global approximation of the Hessian of V star at z. So if you remember, we had this U which satisfied this. Right? And so I have this integer value guy. Okay? And what I do with this guy is I just rescale it down the same way this guy is rescaled. Right? So I just define this U bar sub. Well, okay, so if I define this guy to be rescaled the same way V is, okay, then I can take some sort of translated copy of this thing, and it's going to be sort of sitting here like this. Okay, and this is going to be U bar n kj. Okay, plus a little linear factor. Okay. And I can put these two things together and break the least action principle. Right? And that gives a contradiction. Okay, so therefore, we actually know that these two things are equal. Okay, now I'm totally out of time, but the point is, well, the rest of the convergence sort of just follows immediately from this, because the limiting image is just the Laplacian of the limiting odometer function. Yeah.
For convergence, you get local uniform convergence of the V of the odometer functions?
Yes.
And then all you can deduce from that is the weak star?
That's right. That's right. So we know, right, that there's this limiting odometer function, and it converges actually. Well, okay, in a certain sense, it converges uniformly. It doesn't. It converges locally uniformly just because of the singularity that's forming. But actually, we kind of the singularity is very nice. So in fact, if you sort of subtract off the difference between the continuum fundamental solution for the Laplacian and the finite difference fundamental solution, then actually the convergence is uniform.
And then all you can infer is...
Right, so all you can infer is... Right, okay, so you get convergence, and you know that all along the way, sort of the discrete Laplacian is bounded, right? And you're converging to something with bounded Laplacian. And so all you get from that is a weak star convergence. So we don't get anything like convergence of the proportions of the different values. Yeah.
So it looks like up until fairly late in the proof, we don't know that there exist any points where V star has a well-defined Hessian, and then at this stage, there's at least one point.
That's right.
But then at the end, you're saying now that you can't.
Well, okay, but the way the theory actually works is once you have bounded Laplacian, so if you have some function, if you have some function which is continuous on r to the d or some part of r to the d, and you know that this guy is bounded in the distributional sense, then this guy is differentiable twice differentiable almost everywhere.
Do you know anything about the set of non-differentiability for V star? It's got measure 0.
Yeah, gosh, it would be nice to know. Oh, I know it has measure 0, right? But that's what we'd really like to know is that it's just not twice differentiable like on the boundaries of those cells in the picture, right, of the sandpile. So you have these regions where we think the second derivative is constant, right? And it only fails to be twice differentiable on the boundaries between those regions.
But there are also those pattern regions where it's probably also falls on their boundaries.
Which pattern regions?
Periodic pattern regions.
Right. But in the periodic pattern regions, the second derivative is actually still constant in there because those patterns, because they're so regular, they weak star converge to a constant.
Depending on the boundaries of those patterns, it's also
right. On the boundaries of all those regions. So there are all these regions in the image where it's not twice differentiable. I mean, this is what seems to be the case.
So it's got some positive fractal dimension, supposedly.
That's right. It's like it should be like a Sierpinski gasket, basically. Like the boundaries of the Sierpinski gasket, the actual lines.
All right, so Charles is here until Friday?
Yes, right. I'm here through Friday, and I'm happy to talk more about this. Yeah, so I didn't get to the part of the new stuff that we figured out. So Wes and I started working with Lionel after we did this, and we figured out a bunch more kind of more exciting stuff. But yeah, you'll have to come by and ask me about it if you want to know.